Hello, and welcome back to General Chemistry 2. My name is Daniel, and in this video we're going to start talking about how it is that solutions are formed, and then also some of the properties that come out of solution formation. So we're going to start with talking about mixtures and solutions, how we measure the concentration, some of the terms we use that are associated with solutions. Then we'll go into how solutions are formed from a thermodynamic perspective, meaning what makes a solution formation endothermic or what makes it exothermic, and also what are the effects of entropy. Then we'll go into the factors affecting solubility, those being molecular structure, temperature, and pressure. And we'll see how they affect the solubility of our solutes. And then finally we'll go into our colligative properties, which are just properties that arise from the creation of solutions versus a pure solvent. Okay, so let's just start off with reviewing some of the things about mixtures. So remember from early back in Gen Chem 1, we said that unlike a compound, a solution is something that has a variable composition, meaning that you can add more solute to increase the concentration or evaporate some of the solvent to also increase the concentration. You could add more solvent to dilute the solution, so on and so forth. So when we're talking about relative concentrations, we're going to say that a dilute solution has a relatively low concentration of a solute, whereas a concentrated solution has a relatively high concentration. Pretty straightforward. The three major ways we can look at solution concentration mathematically are through these terms molarity, molality, and mole fraction, the equations for which are on the bottom of the screen here. So molarity we're pretty familiar with. That's just moles of solute divided by liters of solution. Molality is something that's new, but it's relatively straightforward. Molality is just the moles of solute over the kilograms of a solvent, meaning that instead of looking at the volume of the total solution, when we're looking at molality, we're looking at the mass of the solvent by itself that's present. And then we're also familiar with the mole fraction. The mole fraction of some substance A is just the moles of A divided by the total moles of whatever is dissolved in the solution. So that one's particularly useful if we have multiple solutes dissolved in a solvent. Okay, so some other terms, we can talk about how solutions are saturated. So saturation of a solution is just referring to the degree to which solute is dissolved in it. And there's three cases. The first case is when we have an unsaturated solution. An unsaturated solution occurs when we have less solute than the total that we can dissolve. What that means then is that more solute could be added to an unsaturated solution because there's more capacity to hold solute in the solvent. When we have a saturated solution, that means we have the maximum amount of solute that we can dissolve in the solvent without any kind of precipitation or non-dissolving occurring. So a saturated solution leads us to the solubility of the solute in whatever solvent we're using. Recall from when we were talking about equilibrium, we had these KSP values and we calculated solubility. That was the maximum amount of those metals that could be dissolved in solution. And then finally, we can also sometimes have what's known as a supersaturated solution. So a supersaturated solution is typically formed when we have a when we heat up the solvent. That's going to increase the solubility of any kind of solid or liquid solute that we add. What can happen then is as we cool down the solution, the solubility is going to slowly decrease. And that means that some of the solute is going to either precipitate or crystallize out of solution. So a supersaturated solution is just describing one where the maximum amount of solute dissolved has been temporarily exceeded. That will eventually go back down by releasing some of the solute from solution, either as precipitate or forming a crystal. If you've ever looked at an organic lab, you'll see that the crystallization process is common in any kind of organic synthesis. Okay, so that was just a review of some of the terms. You should be already familiar with most of that. So now let's look at how is a solution formed from a standpoint of thermodynamics. We can look at it through three different steps. The first step over here is that we have to break apart the solvent-solvent interactions. This is just based on the intermolecular forces of the solvent. We need to do that because to form a solution, we need to have the solute molecules in between the solvent molecules. We have to do the same thing for the solute over here. That's going to be also based on the intermolecular forces. So we have to break apart the solute-solute interactions so that, let's say we have a cube of salt, we're breaking apart the sodium and the chlorine ions from the salt block so that they can dissolve in the solution. And then finally we have our third step over here. The third step is when we're actually forming the attractions between a solute and a solvent, actually forming the solution. And so there's attractive and repulsive forces that occur in between each of those. So what's basically happening here is that step 1 and 2 are endothermic processes. That's because we're breaking apart the intermolecular forces in between the solvent molecules and the solute molecules. So it takes energy to do that. Step 3, this formation of solution, is generally an exothermic process. And that's because we're taking these now separated molecules and bringing them back together closer to one another and forming new intermolecular forces from them. So what we can define as the enthalpy of the solution is just the sum of these 3 steps. And so that will determine whether heat's released upon solution formation or whether heat is absorbed upon solution formation, whether the solution is going to get hot when we add solute or whether it's going to get colder. So this is just another picture describing that, all the same thing. We have delta H1 is separating the solute, delta H2 is separating the solvent, delta H3 is just the forming of the solution from the now separated solute and solvent over there. So let's think about what's going to lead to an endothermic or an exothermic solution formation. It's going to depend on the intermolecular forces of solutes and solvents with one another and with themselves. So let's first think about an endothermic process where the enthalpy of solution is greater than 0. When that happens, what we can say, let me write that down here, if delta H of solution is greater than 0, that means it's an endothermic solution, which must mean that delta H1 and delta H2, the breaking apart of solute and solvent, is greater in quantity than delta H3. So that would lead us to a net endothermic process. The reason for that would be that the attractions of the solute-solute and the solvent-solvent, that is, with the solute with itself and the solvent with itself, are greater than those between the solute and the solvent. That's just a long way of saying this statement here. On the other hand, if we have an exothermic solution, the opposite's true. So if we have an exothermic solution, that's going to mean that the sum of delta H1 and delta H2 is less than delta H3. That would lead us to a net exothermic process. And the opposite is also true with the description. If we have an exothermic process, that's going to mean that the attractions between the solute and the solvent are greater than those between the solute and solvent and the solute and solvent themselves, which is just reiterating this point once again. We can, when we're looking at the thermodynamics of solution formation, we also have to take into account entropy. So the formation of a solution is generally going to be influenced by the entropy change. So what we can generally say is that if we mix a solute and solvent together, that's generally going to lead to an increase of the entropy of the system. And that makes sense if you think about what we're coming from. If we're coming from a pure solute and a pure solvent, and we mix them together, the disorder of that system has increased. So in general, for the formation of solutions, we're almost always going to have a delta S of solution that's greater than 0. There can be some exceptions to this, especially with less ordered molecules and the dissolving of gases, but we'll get into that later. So those are the cases under which we can have exothermic or endothermic. And if we look at this chart, this is just displaying this in a